over the last few years, and I guess I've been labeled the SDN guy. And I think that Sdn technology will be applied to the network. But the discussion is going to be much broader than that. So certainly we'll talk about SDN in the context of how it's applied to a service provider network. But I think there's a number of other disruptive technologies that we'll use to, in fact, change the way we deliver network services. So here's the agenda. I'm going to talk, as I said, first about the network and the business and what's happening to the networks that we're building. The next, I'll give kind of an introduction to Sdn technology. And if you've seen me present this before, normally I do this in 3 hours. So you're going to get the 30-minute version. It's going to be pretty tight. But my cartoon here is intended to suggest that every time I present Sdn to customers, I get 30 different explanations for what Sdn technology really is. And none of them is wrong, and a lot of them are right. But it just means a lot of different things to different people. But I'll attempt to explain at least the history of Sdn technology and then what customers believe the main benefits of that technology will be today. We'll then talk about controllers and agents, a popular slice of Sdn technology, and how you would apply an Sdn controller to a network. And again, what will happen here is you'll end up having controllers in your network that are very domain specific. You'll have controllers for the WAN network itself. You'll have controllers within the data center, and these controllers will communicate amongst each other for the purposes of building services end to end. And the last section is an area called NFV, or Network Functional Virtualization. Another hot topic right now. It's typically associated with Sdn technology, but it's really taking the physical network elements and functions that we have today and virtualizing them, putting them in software, typically on general purpose compute. So for starters, I think this slide's probably obvious to everybody, but I thought it was interesting. I met with Netflix 3 weeks ago in San Jose, and we were talking about what impact they were having, particularly in the US, but these statistics are fairly common in Europe as well. But they're saying, roughly 20% of all US traffic. If you combine that with YouTube, roughly speaking, you're talking about 50% of all the traffic in the US is the combination of YouTube traffic and Netflix traffic. And in Europe, it's roughly the reverse of that, meaning that there's more YouTube traffic in Europe than there is Netflix, typically because of content rights and language barriers. My point here behind this slide is that we're still seeing astronomical growth in the way that network resources are consumed, specifically around bandwidth. And obviously, with this growth, given some of the over-the-top players, the question is really, how do we add more value to the network? How do we take services that may exist in our data centers and our cloud and tie them to network services that we're delivering? And the last is really a talk that I'll have around how we accelerate the way we deliver services in the network. And this is really the focal point for Sdn technology today. It's not really about how we commoditize the network and pull all the intelligence out of the network. It's really customers want the networks to go faster. Go faster in the way that you provision services, and go faster in the way that we introduce new services to the network. So what are some of the trends that we're seeing as far as looking forward and looking out? I think probably the one that most customers are asking about is, what's the impact of 4K video or ultra high definition video to my network? And if you look at what, even with modern video compression technology, 4K video will roughly add or introduce about 15 megabits worth of bandwidth per channel with 4K video, and there's also talk of 8K video as well. So substantially more video traffic will be introduced into our networks, either through over-the-top or delivered as part of a natural network service. The next is we're seeing more and more services being delivered from the cloud. These could be as simple as virtual private cloud services, or more elaborate, like security services that are delivered from a cloud infrastructure, leveraging some of the network function virtualization technology that I talked about earlier. The next is around M2M, and more broadly speaking, the Internet of Everything. And this is really an interesting phenomenon, because with the Internet of Everything and with M2M, we have a much larger number of devices that will be communicating over the network. But those devices are typically not high in bandwidth, but they create a lot of network events. So they require a lot of control plane scale and state in the network, but they don't directly by themselves introduce a lot of bandwidth. We just have an awful lot of them. So my point behind this is that the methods we typically use today, Telnet, SNMP, SSH, to manage network elements and to provision services, those are simply not going to scale. Those were not designed for provisioning services at real time and stitching services together across a data center and a network infrastructure. So a lot of the focus today is around how do we create a standardized interface to the network through an orchestration level that will actually give us the ability to create applications profiles that allow applications to create services on demand. One thing we're seeing is a shift in really where the value of the network and the services lay. And one thing that we've noticed is that over time, more and more services that were typically delivered on physical network elements are being pushed into the cloud. And a couple examples of services that are being pushed on the cloud are shown on the right here. So we're seeing virtual private cloud services, hosting services that are actually being pushed into data centers, where we're interconnecting those in a much smarter way to the network. The next is NFV services, and some examples are here. So you might be surprised to know that we have over 20 different NFV solutions in various stages of development. So anytime you see a physical network device like a firewall, we'll have a virtual equivalent. And we have to provide a seamless way to map the physical network to these virtualized software services. And the next is in the mobile space. So how we actually attach a similar set of services to the mobile network. And these were referred to as GI LAN services. So if we look a little deeper at the network layer, there's some interesting things that are happening. And they're really up against one observation, which is Moore's law, and another physics theorem, which is Shannon's limit. And what we're seeing, and in terms of what we're doing to simplify the network, it turns out that Moore's law is actually running out of steam. So Moore's law suggests that, and it's been quite true for a long time, that every 18 months will roughly double processor power at half the price. And what ends up happening is because that processor technology, like everything, is based upon atoms, as we shrink the ASIC and network processor technology further and further, we're coming up against many different physics constraints. So although we may be able to double processor power, we may not be able to half the power, as an example. Or as another example, although we may double the processor power, the cost of manufacturing, because we're miniaturizing at a very deep layer now, will actually go up. So there's trade-offs that are actually happening from a CPU and network processor perspective. At the same time, we're integrating packet and optical technologies in a much more deeper manner than we did before. And we're introducing something called coherent optics. And coherent optics allow us to play with this trade-off between bandwidth and distance. So we're actually, and this really talks to Shannon's limit, which says, how many bits can I fit per hertz? And we're really right up against that window now. So now we're actually saying, well, what if it was software selectable? So we could say, hey, I might only want to send 10 gig 10 kilometers or 100 gig 10 kilometers. Can I trade the distance and the bandwidth off? And that will be a software selectable function that you'll enable in your network to do trade-offs based in your particular network topology. I think what's also happening from a bandwidth perspective is a move and a look beyond 100 gig. So 100 gig technology is being introduced into networks today. Many operators within Canada are already upgrading their long-haul links and introducing 100 gig interfaces. And within the IEEE, we're actually looking at 400 gig already. So we predict that 400 gig, we'll start to see initial samples of that technology in the 2017-2018 timeframe. So we're really looking at, okay, now if we've done and addressed the bandwidth at the network layer, how do we actually integrate the transport layer, the DWDM technologies to this ongoing network demand? And the last area is around ROADM technology. So again, and I think in Canada we're probably a little ahead of the curve, is removing SONET, because the focus is no longer on SONET or TDM technology. It's around just putting IP as efficiently as possible onto glass. And so we'll see a much tighter marriage between IP and packet optical technologies. Through all of this, we're intending to unite packet and IP technologies through the use of a unified control plane. So the unified control plane will allow us to do things like plan the transport capacity and the IP capacity in aggregate. So we have a clear view of the complete utilization across both domains. So that's a quick run through on what's happening in the network space. And now I'm going to shift gears and talk about Sdn Technology. So this slide I've used several times, and as I said in the beginning, SDN means a lot of different things to a lot of different people. And there's a lot of different types of Sdn technologies and use cases where it gets applied. The original genesis behind Sdn Technology actually came out of Stanford and Berkeley University. And there was a paper and a project called Clean Slate that Cisco was involved in the early days. And it really talked about this decoupling of the control and the data plane. So you actually move the control plane off the network element onto a device called a controller. And at the time, it was thought that this would be a way that we could radically drive cost out of the network. And really, nothing could be, I would say, further from the truth. Most customers today have realized, and for several reasons I'll point out, that I think there's certainly use for a controller in the network, but reinventing the protocols and the technologies we've used for the last 25 years doesn't really make a lot of sense. So the focus is really around now, how can we make the networks go faster? Faster in the way, as I said earlier, that we introduce services and we provision services in the network. So originally we had this protocol that was introduced roughly 4 years ago called OpenFlow. And OpenFlow is what many refer to as a bottom-up protocol, meaning that it looked at the bare primitives that were required to support network element forwarding, and it provided an interface to the network element at the data plane layer. There are a variety of other protocols, which I'll go through quickly, that are probably going to cover a larger majority of SDN use cases than OpenFlow will. I think OpenFlow will have a place in customer networks, but it's likely some of the other protocols will be more prevalent. What most customers are saying is, if you think about the way that the server guys turn up a virtual machine, we want to make it that easy to turn up network services. So we want to kind of get the network guys to move as fast as the server guys in terms of how fast it takes to introduce new services. This obviously implies that we can reduce some OpEx and allow the network functions to operate more as a service. So really kind of driving some of the automation technologies directly into the network. This chart really captures a variety of SDN use cases. So if you look at the top right of the slide around the forwarding use cases, these are really where OpenFlow is optimized around. So I have a particular subset of traffic, and I want to send that traffic to a destination based on criteria other than the shortest path or other than the destination IP. So with OpenFlow technologies, it really works well as an enhanced policy-based routing. So you can say, I want to match on this type of traffic, and then based on this type of traffic, I want to send it to this destination. And I think there's value in that. But more customers I talk to are saying, really what I need is a way that I can go and provision services at real time, get the state of my current running network, and provide a way that I can stitch services across my network end-to-end in an easier fashion. And that's really, I would say, where a large amount of the focus is around orchestration and automation, providing that service template so I can enable and push services into the network much faster. So there's a number of different SDN technologies I've talked about already, but just to kind of level set everyone, again, originally there's this idea of controller-based networking, so I take some of the functionality that's in the physical network today, and I centralize that, typically in software, typically on a general purpose compute device. And then I provide a mechanism for actually deriving state or importing state from the network to that controller. There's another area of SDN technology called overlays. So overlays are not new. We've built overlays for a long time. MPLS, for example, is an overlay. But there's a new set of overlay technologies that's being introduced specifically within the data center domain to address things like layer 2 VLAN scale. So technologies like VXLAN and NVGRE are actually used to increase the amount of layer 2 topologies and layer 3 services that can be delivered within a data center. The next is around NFV, and I'll skip that. There's a fourth area of SDN technology which talks about programmability. So give me an API to my device and not an SNMP MIB. Why do I want an API? Because I can drive the API harder and faster than I could with SNMP. If we think about virtualizing all these network elements and layers, we're going to have more state and more elements in the network. And SNMP simply won't scale for the kind of state that we're talking about. So we're working on common APIs either based on vendor-based APIs like Cisco's 1PK, or based on industry standard APIs like NetConf and Yang. So I think we'll see some combination of APIs available on all network devices. And the last area is OpenStack. And OpenStack gets thrown and included a lot with Sdn Technology. Frankly, it can be used with Sdn Technology, or it can be used without Sdn Technology. But the genesis of OpenStack was really an open source orchestration solution that Rackspace and NASA came up with, so that they can come up with an automated way for provisioning, storage, and compute. And Cisco's contribution was to introduce a network module to OpenStack so that we could provision network-based services. So let me go through a little bit more detail on what a controller is. So if we think about the way that networks were designed, we've obviously distributed network functionality out in the network, and we've done that for a very good reason. The internet obviously works based on the fact that network intelligence is distributed. So if we have a failure in the network and we've distributed all the protocols in the network, we can react really quickly to any changes if a link fails or if a box fails in the network. It's been written in several papers since the original introduction of OpenFlow that this approach really won't work. But it's important to grasp this concept because a lot of customers are still thinking, well, I'm going to actually take my routing protocols I have today and put them on one big software-based server in my data center and run BGP from there. And that's just simply not the case. However, so there's clear benefits for a distributed control plane. However, there is huge value in having a controller on the network. And the main reason I think is having a controller on the network that's interacting with the current network state gives you this ability of saying, hey, if I need a path from A to Z with a certain amount of latency, which path should I take? So rather than visiting every network element hop by hop, if I have this thing called a controller in my network and it has a global view of the entire network, then it makes it much easier to look at those kind of decisions and figure out where I should place a particular demand. So we believe having controllers in the network is certainly of value, and we're looking at a number of solutions and use cases where we'll use it. So there's clear benefits for a centralized control plane as well. So I think what you'll see is controllers being used in a hybrid model, where the existing technologies you've used to run the network to date are intact, but we add controllers to the network. And it's likely we'll add controllers that are very domain specific, perhaps that are very service specific, and we'll probably add multiple layers of controllers because they're centralized and we now need redundancy for those controllers. So it's likely we'll have multiple controllers in their network, and their function is really to interact with the network and figure out a way that they can look at the entire network picture so that when we introduce services, they have that clear view of what the network state is end to end. So a northbound side of a controller, is just an API that sits on top of the controller that applications can interact with. So you'll write applications to the controller's API. Vendors will provide applications along with their controller. But the intent is that the functionality that exists in the network is now exposed through an API that's delivered through the controller. The other important part of a controller is the southbound interface and how you actually interact with the network. And there's a variety of protocols that will be used southbound from a controller to the network. And those include technologies like OpenFlow, like I2RS, like Pset, like vendor-specific APIs. And you may use any number of these depending on the service or the function you're trying to deliver through a controller-based model. So what we found kind of in the early days, I'll say, although it's all relatively early days with Sdn Technology still, is that we really wanted to standardize the controller ecosystem. If we had everyone building their own controller framework, it would be very difficult for customers to buy applications if the controller was different, because you'd have to use the same controller for a given application because the APIs would all be different. So a number of vendors within the industry got together in an open source effort called Open Daylight, and they contributed different components of their in-house developed controllers and standardized the controller technology itself. So the advantage here is that everyone's using the same building blocks, if you will, to build a controller, and we have a much structured method, an interoperable method for allowing customers to choose applications that run on a common controller framework. So you can see there's a link to Open Daylight, and this is a free public domain open source controller that can be downloaded and up and running, within 5 minutes. It's quite easy to install. I mentioned already that I think what we'll end up seeing is controllers that are very domain specific. And one example of that is a WAN controller. So we believe what you'll see is a WAN controller sitting out on your network, gathering state from the network, and building up a topology of the network. So we can play those what-ifs analysis scenarios, but also so we can collect analytics from the network. We can build a traffic matrix from the network, and we can say, you know what, between nodes 1 and 7, we've got this amount of traffic between 9 a.m. and 10 a.m. of every day. So we can collect that utilization information across the network and aggregate that up through a centralized entity that now my management tools can interact with. So this is a good slide that really captures all the southbound protocols that I believe will be leveraged from an SDN perspective. So we really started with OpenFlow, and within the ITF, we're standardizing a new technology called I2RS, stands for Interface to the Routing System. Essentially, it's an API for all the layer 3 functions in your network. And this has actually got a lot of industry momentum. And from a service provider perspective, I think probably this will be one of the most important protocols that will be used in the near future. We've got a number of other protocols. One's called Pset. It allows us to extract state about LSPs in the network or specific flows within the network. Again, gaining a lot of traction within standards bodies, and most vendors have plans to implement Pset. And you'll see there's a number of other protocols, including Quantum. Quantum's now been renamed to Neutron. It's the plugin that goes in OpenStack that actually controls the provisioning of network services. It may surprise you, for many years, we've actually been building software equivalents of all of our operating systems. And so we intend to deliver a software equivalent of iOS or iOS XR to run in an NFV type environment. But more so than routing as a service, we'll additionally offer other functions and services like DPI, like firewall, like NAT services. And these, again, can all be delivered as an NFV type service from a data center. I think the trick is how you actually connect those NFV services to the network. And this is, again, an area of great innovation right now. So within the standards bodies, there's a working group that's being formed around network service chaining. And network service chaining is really, okay, if I've got traffic that's coming into my data center, I don't want to build a physical network topology for every service. What I really want to do is I want to say, let's forward that traffic from this virtual machine that's running a particular service to this other virtual machine to this other virtual machine. So these network services are now no longer directly physically connected, nor do I have to build a logical topology. I don't have to build a VLAN or a VRF to introduce new services. I'm actually using service chaining at the data plane layer to say, okay, take the traffic from customer A, and based on his policy, send it to this host, then send it to this host, and send it to this other host, and then punt it back out to the internet. So combining NFV services with a technology called network service chaining will allow us to introduce network services much more efficiently. And again, I think what we're looking at is distributing many more typical routing functions directly within the data center. So functions that may have existed on a managed CPE, for example, we can now move those network services to the data center and deliver them from the data center. So we get an ability to introduce services much more rapidly than we could in the physical world. And so my last slide, just to wrap up, is I believe that we've seen a change in the way that customers will leverage Sdn technology. And most customers are saying, you know what, I've got a network today, it's working perfectly fine, but I really need a way that I can introduce new services to the network in a much more rapid fashion. So we believe a hybrid model where Sdn technology will be applied incrementally to networks to solve specific business functions and provide a much easier way to introduce services. So that's all I had. Okay. Do we have time for questions, or do you have a? Yeah, we have a couple minutes for questions. Okay. Oh, there we go, sorry. Hi.
It's Ron Hoseman from Allstream. Well, I certainly see the benefits of the SDN and opening up the control plane, so to speak. What about the security aspect of it? Networks are inherently secure today because of the limited access to the control plane and the routers themselves. Seems like it opens up a big door.
I don't know if it, so certainly the southbound protocols themselves, I would agree with you that there probably hasn't been enough focus on, for example, on security and OpenFlow as an example, as there's been with kind of the legacy of other traditional routing protocols. Like we've done a number of security enhancements, for example, with BGP over time. It's not had that maturity at this point yet. So it's a fair point. I think with I2RS, there's a lot of work going on from a security perspective with that protocol. But it still is early days, quite frankly. So, you know, in terms of mass SDN deployments, the biggest one that everyone points to is Google. And Google built their own routers. So they're kind of a different use case. But, you know, just from a deployment perspective, a lot of customers in Canada are looking at Sdn Technologies, but it's in the very early stages. But I think we'll have to examine security in more detail. Any other questions? Good. Thanks very much.
Thank you very much.
Yeah.